So we have seen how to add and subtract vectors using graphical method. Now let's look at another way of doing vector algebra by first turn vectors into numbers so that instead of drawing, we can just perform numerical calculation to add and subtract vectors. In order to do that, we have to first turn vectors to numbers. And let's see how we can do that. For simplicity, let's first restrict ourselves to 2 dimensions. So the vector is, say, in XY plane, in just 2-dimensional plane. Now, a vector has a starting point and an ending point. As we learned before, though, it doesn't matter where the vector starts. I can move a vector from one place to another by moving its origin, by moving starting point, as long as I don't change the magnitude or the orientation, it is the same vector. And because of that, why don't we start every vector in the 2-dimensional plane in the same point, at the same point? That way, we don't have to worry about where it starts because it's always the same point. We just have to worry about where it ends. Okay, let's say I'm going to label a point, the end point as point P. So I'm going to call this point P. That's the end point of a vector. As long as I know what point P is, this vector is uniquely identified because I know where it starts and I know where it ends. Now, how does one uniquely locate the position of a point on a 2-dimensional plane using numbers? Now, we know in 1 dimension using numbers, we have to establish an x-axis, right? And we choose the origin and then the number x, which represents how far the point is from the origin with a positive and negative sign, will tell you uniquely where that point is, right? Now, in 2 dimensions, we do something similar. We introduce an XY coordinate system. That's what we do to turn the designation of location of a point into numbers. So let's establish a coordinate system. And where do you suppose I want to put the origin of that coordinate system? Well, might as well put it at the location where every vector starts, right? Because that's just for convenience. You don't have to, but we usually do that. So let's draw an x coordinate like this, okay? And a y coordinate also passing through the beginning point of that vector. So we call this x and this y-axis. So every vector by convention starts at the origin of the coordinate system, which we label as point O here. And then the endpoint P acquires a pair of coordinates, x and y. Okay? And once you know x and y, then point P is uniquely identified, the location of point P. And therefore, this entire vector from O to P is also uniquely identified. And this means that once I know these 2 numbers, x and y, you give me these 2 numbers in 2 dimensions, I can find this vector for you. This vector is then uniquely identified, vector A. I'm using this symbol here. It means there's a 1-to-1 correspondence between this vector A and this pair of numbers, x and y. Okay, x is the x coordinate of the endpoint P of this vector. Y is the y coordinate of point P. But you know, that's not exactly what we want at the end. Because in order to do, say, a plus b or a minus 3b and so on, I want to express A in terms of x and y, not just as a correspondence, but as an actual equality. What I want is A as a function of x and y. I want an equality, okay? Equality. On that side, you express in terms of x and y. It's not a correspondence. So how do I upgrade the correspondence sign into an equal sign? Okay? That is what I need to consider. So how do you go from here to there? To do so, we have to go 1 step further. And that is, we're going to break this vector down into 2 simpler vectors by using graphical addition of vectors. Now we know if you draw a vector triangle, you can start with 2 vectors and as two sides of a triangle, and a third side will be the sum of the first two vectors if you position them correctly. So let me show you how we do that. This vector A, I'm going to break it down to two simpler vectors. They're simpler because I know precisely their direction already. Okay, one is along the x direction, the other is along the y direction. So this is what I'm going to do. I'm going to take the first of these two vectors to be along the x direction. Okay, so I'm going to draw something like this. Okay, so here's a green vector. And now I'm going to also draw another vector to complete this vector triangle. And this vector is on the y direction. On the y direction. Clearly, if you understand anything about how to add vectors graphically, as we learned in a previous lecture, the vector A is equal to the sum of the green vector and the purple vector. Right? Now, but there's something special about this green vector, and that is it's oriented along the x direction. So how does one express this green vector? You know, this green vector has a direction which you already know. It's got a magnitude which is equal to what? Which is equal to the length between this point and this point, right? This, by the way, isn't that just x, right? X is the x coordinate. The point P is also the length of this green vector. If you look at how what x really stands for, right? So this length is just x. Similarly, for the y component, for the y coordinate, we know the length of this purple vector is actually just equal to y. It's just equal to y. Okay, the length of this purple vector. As a matter of fact, if I were to draw a line connecting point P with the y-axis parallel to the x-axis, I'm going to get something like this. This length, as you know, is y. And that length, as you know, is x, right? That's what coordinates x and y really stand for. So therefore, as far as this green vector is concerned, it has a magnitude of x. It's got an orientation along the x-axis. And if I were to introduce what's called a unit vector along the x direction, okay, a unit vector. That's a very important concept. We have to use that in order to proceed with vector analysis, vector algebra using numbers. Unit vector along the x direction, I. I is a vector, and I typically use a cap to indicate it's not just any vector, it's a unit vector, meaning that its magnitude equals 1. I is defined such that the magnitude of I, which by the way, we put it in absolute sign, is defined as 1, and along the x direction, along the positive x direction. This is what I define as a unit vector along the x direction. So here is the unit vector, like this, that's I. If I define I like this, then what's the difference between I and this green vector? Look, they have the same direction, right? The only difference is their magnitude. Okay, instead of having a length of 1 unit, the green vector has a length of x units, and therefore the green vector is just x times I, isn't it? Right, so this green vector I can write as x times I. Okay, that's the green vector. In the meantime, I do the same thing in the y direction. I'm going to introduce a unit vector along the y direction, like this, and we call it j. It's the same, if I move it to here, it's the same unit vector j, okay? It's got the same direction, same magnitude as I, which is 1 unit. So j also has a magnitude of 1 unit, but it's along the positive y direction. Okay, and if you do that, then I can easily express the purple vector as y times j, because the purple vector has the same direction as j, except it's y times as long. All right, so now we have successfully broken this vector A into two simpler vectors, xi and yj. And if I add these two vectors up, don't I get just vector A? So I finally have the following identity not just the corresponding side, and that is A equals to xi plus yj. Now this is what I'm really looking for, because it's an equal sign in the middle, not a corresponding sign. Okay, you give me a pair of numbers x and y, I can express this vector for you with the help of a coordinate system and unit vectors I and j. Okay, in this new context, the number a is called the x component of the vector a, and the number j is called the y component of the vector a. What is so special about this expression? Because once I do that, and that is I take a vector and break it down into x component and y component, then I can add this vector to any other vector if I know the component expression of the other vector. I can do a plus 3b, b minus 4a, whatever. As long as I know the component expressions of x and y, of a and b, I can do that, right? Just simply calculation. Now, before I do that, I have to make sure that we all agree that once you know these two numbers, x and y, you can uniquely specify this vector, and vice versa. And that is, once you know the vector, you can uniquely specify x and y. Okay, this is realized in the following two pictures. You can see here in the first picture on the right, I have this vector a, and I broke it down into two components, a sub x and a sub y. It's just the same as the x and y I've been using before. Okay, so given a sub x and a sub y, two components of the vector a, can I identify this vector? Now, when I say identify this vector, what I really mean is I want to find both the magnitude and the direction of the vector a. So can you find the magnitude of the vector a once you have ax and ay? Yes, of course. Look, you have a right angle triangle here, right? With two sides, ax and ay of length each, and the hypotenuse has a magnitude a. And Pythagorean theorem then tells you that a squared equals ax squared plus ay squared, and therefore I say I can find the magnitude, which is the square root of ax squared plus ay squared. I can also find the direction by specifying the angle theta. We know tangent of theta is ay over ax, so tangent of theta equals ay over ax. So give me these two numbers, ax and ay. I can find the magnitude a for you. I can find the angle theta this vector makes with the x-axis, therefore specifying the orientation of the vector. Now here, actually these two formulas are written on the right side, so probably better for me to move these formulas to the right side. So let's do that if I can. Let's move it to the right side. Okay, but so that is how you get the information about this vector, the magnitude and direction from the components, ax and ay. But I can do the other way around. That is, given the magnitude and direction, that is given a and theta, can I find ax, can I find ay? The answer is, of course, yes. Again, you look at the right angle triangle here. How do you find ax? Well, ax, isn't that true that ax over a equals cosine theta, and therefore ax equals a cosine theta. And similarly, ay over a is sine theta, so ay is a sine theta. Okay, so this, the diagram on the left-hand side tells you how to go from the information about this vector to find its components. From the magnitude and orientation, you find the components. And the one on the right does the other way around. Given the components, ax and ay, you can find the magnitude and orientation of the vector. So clearly, there are one-to-one correspondence. All right, now we have successfully expressed vectors as numbers, a two-dimensional vector corresponding to two numbers. One is the x component, the other is the y component. All right, now let's look at an example how we can use that to express the position of the displacement vector as an example using numbers. So here is a map of the Bay Area. You start from San Francisco and you draw a displacement vector from San Francisco to Sacramento, and you find that the length of displacement vector S is 123 kilometers. And if you draw an east-west baseline, you find that this vector linking San Francisco to Sacramento is at 45 degrees above the x-axis. The x-axis being from west to east. So let me draw a coordinate system out from a diagram using San Francisco as which is the beginning point of the displacement vector, as the origin of the coordinate system. So let's do that. Okay. So here is the x-axis, and then draw the y-axis perpendicular to that. That's north and west. That's north and south. So here is the north, south, the y direction. All right. In this coordinate system, the displacement vector linking San Francisco to Sacramento, can I find the components of this vector? Okay. What is the x coordinate? S sub x, otherwise known as the x component of the vector s, the x coordinate of the end point, which is right here, Sacramento, right here. Okay, can I find the x component of this vector s, or can I, similarly, I can say, can I find the x coordinates of the end point, which is the location of Sacramento? The answer is yes, I can. I can write S. I can write S as the sum of x, sxi, and syj. I is a unit vector pointing from west to east along the positive x direction. J is a unit vector in the y direction pointing from south to north. Okay, so what is Sx equal to? That will be equal to the magnitude S times what? Cosine of this angle, which we call theta. Cosine theta. Okay, now S is 123 kilometers and cosine 45 degrees. It's interesting that this angle is actually 45 degrees. Anyhow, you get about 95 kilometers. Similarly, Sy. The y component of this displacement vector S is S times sine theta. And that'll give you also 95 degrees, because at 45 degrees, the S1 components are equal to each other. So I have expressed this vector pointing from San Francisco to Sacramento in terms of two numbers, 95 kilometers and 95 kilometers. You know what that means? It means that if I start from San Francisco and if I move east by 95 kilometers and then I turn north, I move north by also 95 kilometers, guess where I end up with? I will end up at Sacramento. Okay, so this is an example of how to express the position of a vector in terms of components. Now, so far we have dealt only with one vector, expressing it into xy components. But again, the big reason why we introduce this what's called analytical expression of vectors, and that is to turn vectors into components, into numbers, is because we want to do vector algebra, and that is we want to add and subtract vectors. So how do we do that? Using analytical method. So component expression in 3D case, that's something we should also study. Let's come back to that a little bit later. What I want to talk about first is how we express the sum of two vectors using components. Okay, so here is a graphical representation of what we can do. Suppose I have a red vector A and a blue vector B. Each has its own components. A has two components, A sub x and A sub y, as you can see here. B similarly has two components, Vx and Vy. Then I want to do A plus B, the resultant vector R. Okay, if I know the xy components of the vector R, then I know the vector R precisely, right? So you can see clearly from this diagram how we find the x component of vector R. Now, the x component vector R is this length. Let me draw it. It is actually this length from here to there, right? That's the x component. Isn't that the sum of ax and bx, right? The sum of this segment and this segment, right? Similarly, the y component of the vector r is from here to there. But isn't it the same as this length plus that length, which is ay plus by, right? So you can see clearly that r, if r equals a plus b, if vector r equals vector a plus vector b, you can see clearly from the diagram above, then r sub x equals to a sub x plus b sub x, and r sub y equals a sub y plus b sub y. That's what we saw from the diagram. Now, we can easily show that by using the expression that we just obtained, and that is, I know what a is. A can be expressed as a sub xi plus a sub yj, and then similarly, b, I can write it in component form b sub xi and b sub yj, right? And therefore, when I do a plus b, I can simply, without drawing anything, I can just simply plug in a equals this, b equals that. So here is axi plus ayj, and then plus bxi and byj. Right? Now, let's add these two vectors together. Let me add this guy and this guy together. Why? Because they're in the same direction. When you add vectors in the same direction, you just add their magnitudes up, right? Just like, you move forward by 2 miles, then move in the same direction by 1 mile. How far did you move? 3 miles, right? In the same direction. So you add these two together. Isn't that just ax plus bx? Okay, you just take that I out. And similarly, you add ayj and byj. They're again two vectors in the same direction. Isn't it just ay plus by and j? Okay, so therefore, the x component of the resultant vector is right here. And that's r sub x. The y component of the resultant vector is right here. That's r sub y. So clearly, you see, again, r sub x equal the sum of ax and bx, r sub y equal the sum of a1 and by. And that is when you have two vectors. What if you have three vectors? Just keep on adding the components. The same, add all the x components up to get a resultant x component, add all the y components up to get a resultant component. So no matter how many vectors you have, as long as you know their components, you can simply do addition and subtraction of the components. You can find the x component and y component of the resultant vector, which means you know precisely anything you want to know about the resultant vector. Okay, you can even do, say, 3a plus 4b. Why not? Because you have to multiply 3 in front of both ax and ay to get 3a. Right? 4b, just multiply 4 in front of bx, in front of by. You can do 3x plus 4b. You can do 10x minus 3b. Whatever you do. As long as you're doing the vector additions and subtraction, as long as you know the components of each vector, it's a matter of simple addition and subtraction. So this is a big reason why we break vectors down into components, okay? Because the vector algebra, addition and subtraction, becomes very simple to do. Now, we'll look at some more practical examples of that in our next lecture. But before we end our discussion for this lecture, I want to go back to this table, to this diagram. I want to look at what happens in a three-dimensional situation. We've so far discussed only two-dimensional component expressions. In 3 dimension, you have two commonly used coordinate systems. You have xyj, xyz, Cartesian coordinate. You can also use the spherical coordinates that are also frequently used. Now, in a spherical coordinate, okay, you're given two numbers, two angles. This angle starting from the z direction, going down until you meet this vector, and this angle is typically called theta. You have another commonly used angle starting from the x-axis until you meet the projected line of the vector onto the xy plane. So that is the angle called phi. Of course, you're also given the magnitude of the vector, okay, which is a, the magnitude of the vector. Look, in 2 dimensions, you need 2 numbers to specify a vector. In 3 dimensions, you need 3 numbers. These 3 numbers could be the 3 components on x, y, j. That is, you're given ax, ay, and az. You can also be given, in the spherical coordinate, 3 alternative numbers: the magnitude a, the angle theta, and the angle phi. Now, if you break it down into ax, ay, az using Cartesian coordinate, it's very simple. We can easily write that down. Vector a equals, instead of a sub xi plus a sub y j, all we need to do is to add 1 more component in a z direction. That's a sub z. What's the next letter after I and j? That's k. So introduce a unit vector along the z direction we call k. As you can see here, this is the unit vector along the z direction. Okay, hang on, here's along x direction, along the y direction. Okay, so this is how you break it down into 3 components in the Cartesian coordinate system. But we can also express this in terms of the 2 angles theta phi and the magnitude a. How do we do that? Well, often this is quite useful. Here's how we do that. We just need to know how to express, how to rewrite ax, ay, az in terms of these 2 angles and the magnitude of the vector a. For example, this, let me label ax on this diagram. Okay, ax is this length right here. This is a sub x. Let me find how to express this in terms of a, theta, and phi. Now, if you know this length, that's the hypotenuse of a right angle triangle, right? If you know this length, you also know the angle phi, then I can find ax, right? And this length really is this is the shadow of this vector projected onto the xy plane, right? If you start with this 3-dimensional vector and imagine you cast a beam of light from the z-axis downward like this, it's going to drop a shadow for this vector onto the xy plane. And here's the shadow right here. This is the shadow. Okay, that's the shadow. And so how long is the shadow? Well, look at this vertical right angle triangle here. This vertical right angle triangle. Let me highlight it. This one. Okay. This vertical right angle triangle has a hypotenuse, which is the magnitude a. And it has this angle here. Has this angle here, which of course is the same as theta. Right? So therefore, this line here has a magnitude of what? Of a times sine theta. Okay, a times sine theta. Right? So this magnitude is a sine theta. And then I multiply this by cosine phi. That's how I go from the hypotenuse to ax. So multiply by cosine phi. That is a sub x. Okay, now similarly, I can find a sub y. A sub y really is just this. Right? So it's the same horizontal right angle triangle, except I'm looking for the other side. And so therefore, it is not cosine phi, it is sine phi. A sub y. The same hypotenuse, a sine theta, but multiplied by sine phi. Okay, because it's the opposite side of the angle phi. So that's ax and ay. Finally, az. You realize that az is just same as this. That's az. And that's quite simple. You start with the hypotenuse a in the vertical triangle. And this is the adjacent of the angle theta. So therefore, az equals to a cosine theta. Okay, so you plug in these 3 expressions, ay, ax, and az, into the component expressions for a. You can now express the 3 components of the vector a in the variables of a spherical coordinate system. Instead of x, y, z, you now have magnitude a and then the 2 angles theta and phi. And oftentimes we find this expression quite useful because oftentimes in 3 dimensions, we're not given x, a, y, z. Rather, we are given the 2 angles and the magnitude of vector A. In a discussion that you'll be doing later, you'll be studying the Earth's coordinate system, the longitude angle and the latitude angle. They are very much related to our discussion here, especially the latitude angle. Okay, both the latitude and longitude angle, they are related to the angle theta and phi. And you can simply do a little bit of modification and you will get the expression using these 2 angles, latitude and longitude angle. I mean, in fact, this angle is the same in the convention of latitude and longitude coordinates, labeling system. This angle is the same. It is called the longitude angle, but the latitude angle has a different definition. We start from the equator going up. Okay, the XY plane is the equatorial plane in this labeling system. So we call this angle going up from the equator as the latitude angle instead of theta going down from the North Pole. But that's just a matter of changing, theta to 90 degrees minus theta. Otherwise, it's really the same. Okay, and you'll find this to be quite useful if you try to understand, what these 2 angles mean, so you can find the location of any spot on the surface of the Earth. So again, in this lecture, we introduced a way of turning vectors to numbers by introducing first of all coordinate system, and then breaking down a vector onto using its components, xy components. And this gives us an easy way of adding vectors and subtracting vectors. And in the next lecture, we're going to put this to use. We're going to look at how to find a resultant vector if you know 2 other vectors in a real world situation.